A little look at our homework that we had since Wednesday, actually. Worksheet number 5. We had questions number 1 through 8. We'll do all 8 of those. They should go pretty quickly for us here. In both of these sets of questions, 1 through 4 and 5 through 8, we have velocity time graphs. You should recognize what type of graph you have, position time graph or velocity time graph. We've seen both now, right? Position time and velocity time. Okay? The way we think about them is similar, but the way we calculate something or determine something is different. So when you get a quiz, you get a test, make sure you identify, at least in your mind, if not making a note on your page, what type of graph it is, position time or velocity time graph. I'm telling you right now on your unit test, you will have a graph and you will have to do a bunch of stuff with it like we do on this worksheet. I'm not telling you whether it's a position time graph or whether it's a velocity time graph, but you're going to get one of them. I'm also telling you on your final exam, you will also get one. You'll also get a graph where you have to do a bunch of stuff like this. Nothing that we haven't done. Okay? You guys are good at the position time graphs. I suspect you're good at the velocity time graphs. But when we see that question on the test or on the final exam, some people will mix the two graphs up and start doing the wrong things because they're getting mixed up. Okay? Pay close attention. Know what you've got. Okay? I think we get that boxed off in red in the back, RTQ, ATQ. What does it mean? Read the question, answer the question. If it's position time graph, know that it is and answer it based on that. If it's velocity time graph, know that it is and answer it based on that. All right. Question number 1 on this velocity time graph. We want to determine the velocity at 6 seconds. How do we find the velocity on a velocity time graph? What is it, Blake? Up and over. Same as it is for position on a position time graph, or the same as it is for momentum on a momentum time graph, or the same as it is for force on a force time graph, or anything else. If you're trying to find a variable that appears on the y-axis, just go up and over. So at 6 seconds, we go up, we go over, and it looks to be about 5 meters per second here. We're not worried about sig figs here. Okay, just say 5 meters per second. Up and over. Calculate the change in velocity between 0 and 9 seconds. Change in velocity on a velocity time graph is like change in position on a position time graph. What are you going to do? What are you going to do here, Scott? Yeah, up and over twice, right? You're finding final velocity minus initial velocity. So up and over twice. At 9 seconds, okay, we go up to 9 seconds here, go up and over, looks to be about 7 meters per second. At 0 seconds, well, my velocity is just 1 meter per second. So we subtract those two, and we get 6 meters per second. Want to find the acceleration? Well, there's 2 ways we can think of this, but they boil down to the same thing. One of them is the slope. We can find the slope of this line using rise over run, right? Delta y over delta x. But what's the other way of thinking of it, which gives you the same thing? Why don't we just say A is equal to delta V over delta T? That is the slope, right? Slope is equal to delta Y over delta X or delta V over delta T. Delta V we already just calculated, 6 meters per second. Delta T over the entire trip there is 9 seconds. So that's going to be 0.67 meters per second squared. And the displacement, okay, this is the toughest one. This is the one where people get mixed up on the most. Okay, sometimes when we see a position time graph on a test or an exam, people, for a position time graph to find the displacement, want to do the same thing as they do here. How do you find the displacement here, by the way? Lucas? Yeah, you find the area. But if it's a position time graph, you don't find the area, right? It's just final minus initial. It's up and over times 2. So know, again, what graph you've got. If it's position time graph, up and over, subtract the 2. If it's velocity time graph, you've got to find the area. Now, this one is a little bit icky because there's 2 shapes here. You got a rectangle and you got a triangle. We've got to find the area of the first one, which is a rectangle, base times height. The base goes from 0 to 9 seconds, so the base would be 9 seconds. And the height goes from 0 to 1. So the height would be 1. That gives me an area of 9 meters. There's the first one, the area of the first one. The area of the second one's a triangle. You guys remember the equation for the area of a triangle? The area of a triangle, Martin? Yeah, it's a half base times height. Sometimes we say base times height divided by 2. Base is, once again, 9 seconds. The height is from 1 to 7. Pay attention to this, guys. It's from 1 to 7. So the height is 6 meters per second. See that? Okay, this is 7. So my height's not 7. The height of that triangle is 6 because it starts at 1. The area of that, 1/2 base times height, is 27. Now we're going to add these up, and we get 36 meters. Now, you weren't asked to find this, but you could have been. What if we were asked to find the final velocity? Sorry, not the final velocity, but the average velocity. What if you were asked to find the average velocity here? Hopefully this isn't crazy hard for you at this point. How do you always find average velocity? Displacement over time, right? We just found the displacement, right? So the average velocity would be 36 meters divided by 9 seconds, which is 4 meters per second. All right, let's take a look at the next graph. What's happening in this one? The velocity is to the north the whole time. Hasn't changed direction. It's not going backwards. It's just slowing down, right? It's decelerating. It's constant negative acceleration. You drive into Calgary, you're going north. You're going north the whole time. But when you slow down on your first set of traffic lights there, going up McLeod Trail and DeWinton there, you know what I mean, Heritage Point. Okay, you slow down to stop at those traffic lights. You're still going north, but you're slowing down. Your velocity is decreasing. The velocity at 6 seconds, what are we going to do? Up and over, and that works out to be 4 meters per second. The change in velocity between 0 and 8, up and over, subtract the 2, right? So we're going to say at 8 seconds, it's 0 meters per second minus 16 meters per second. Remember, guys, it's not good enough just to say, 16 minus 8. Like, you got to do final minus initial. Like, be conscious of that. What is the final? It's not 16, it's 8. Or sorry, it's 0. What's the initial? It's not 0, it's 16. So it might be easier for you to say 16 minus 0, but that's wrong. It's 0 minus 16. Question 7, I'm not going to flip the page because I want to see the graph there. Question 7 says, what's the acceleration of the object? The acceleration can be found by the slope, it's fine, or it can be found by delta V over delta T. Just found delta V, it's negative 16. And the time interval here is 8 seconds. Nice easy math here, negative 2.0 meters per second squared. And 8 asks us for the displacement. Good news, it's a triangle. By the way, when you're using the equation for the area of a triangle, does it have to be a right angle triangle? It is a right angle triangle here, right? But does it have to be? No. No. If you saw one like this, that's a triangle. You could find the area of that using one equation, 1/2 of the base times the height. That'd be okay. If some people think to do 1/2 base times height, you have to have a right angle triangle. You're getting mixed up with sine, cos, and tan. You have to have a right angle triangle to use sine or cos or tan, but not to do, or to do the Pythagorean theorem, but not to do the area of a triangle. Okay. This is the displacement of this one is 1/2 base times height, which is the area, which is 1/2 of 8 seconds is the base, and the height is 16 meters per second. Do you know why we get an area that's in meters here? Look, half times 8 times 16 is 64. Seconds times meters per second, right? Base times height. What's seconds times meters per second? Seconds cancel, and I'm left with meters, 64 meters. So the area is, in fact, displacement. A question just asked, would the 64 be negative? No, it would not be negative. The 64 would not be negative. We calculated this. The area was above the x-axis. It is positive. And let's think about, in practice, like in real world, why it would be positive. I'm going north the whole time. I'm driving towards Calgary the whole time. I'm slowing down, but I'm driving towards Calgary the whole time. My displacement isn't going to be south or negative when I'm driving north the whole time. Does that make sense? If you saw a graph that looked like this, and you wanted to find the displacement, you'd calculate area 1, and it would be positive something. You'd calculate area 2, and it would be negative something. It would be negative something because the velocity is negative, and you're going in the negative direction. It would be going north, slowing down, slowing down, slowing down, stopping. Now you're going south. So you would have a positive or north displacement and a negative or a south displacement. Then you just combine them, right? Add them together to get the total displacement. Does that make sense? It's only ever going to be a negative displacement or a negative area if it's below the x-axis. I think on your worksheet there is a question later on that involves that. Doesn't happen often for us, but it does from time to time. So just keep an eye out for that. All right, what I'd like you to do now at your desks is take a look at the next 8 questions. We're looking at questions 9 through 16. 9 through 16 this time, please. Let's have a look at 15 and 16. 15 says, what's the displacement? 16 says, what's the average velocity? Displacement's obviously the hardest part. A lot of confusion over this. I understand that. That's normal. When you're finding the displacement, you're finding the area. But you're finding the area always between the line and the x-axis. This is the line right here. You're finding the area between that line and the x-axis. This is a rectangle. This is a triangle. This is a triangle. You're not finding this area down here. That's not between the line and the x-axis. That's outside of everything, right? You're finding the area, number 1, because it's between the line and the x-axis. Number 2, because it's between the line and the x-axis. Number 3, because it's between the line and the x-axis. So you're finding 3 areas here, 1, 2, and 3. Does that make sense? Area 1, it's a rectangle, base times height. The base of that, a little hard to see there with my markings on it, but the base of that is 2 seconds. The height of that is 10 meters per second. We multiply those, we get 20 meters. Area 2 is 1/2 base times height because it's a triangle. 1/2 of the base. The base goes from 2 to 7, so the base is 5. The height is 10 again. 1/2 of 5 times 10 is 25 meters. And then area 3, that's a 1/2 base times height as well because it's a triangle. The base goes from 7 to 15, so it's going to be 8. And the height goes from 0 to, what is it, CJ? Negative 20. So that's going to give me an area of, what is that, negative 80? Right? We add those up. 20 plus 25 plus negative 80 gives me negative 35 meters. So we do have some positive displacement there, but overall, the displacement is negative. In other words, we end up to the west overall. Now, we find the average velocity. This one's easy now compared to what we just did. It's displacement divided by time. The displacement we just found to be negative 35 meters, and the time here from 0 to 15 seconds is 15 seconds. Divide those and we get negative 2.3 meters per second. Is it going a negative velocity the whole time? No. Here it stopped. In not stopped. In number one, it's a constant positive velocity. In number two, it's a decreasing positive velocity. In number three, it's a negative velocity, an increasing negative velocity. The overall average velocity is negative because in the end, we're in that third stage longer, right? We're going in negative velocity. We're going backwards for longer than we're going forwards, right? For 8 seconds versus 7 seconds in a higher velocity. Does that make sense? Now, we didn't have to find the acceleration of any of these, but if we did, then we would just say delta V over delta T or the slope again. All right, if you had trouble with any of the questions, go back and try them again now after going over questions 15 and 16. Your only homework for the weekend, and you're probably, for the most part, done it already, is up to number 16 on that worksheet.